Hi, this is Chenyang Zhao from University of Southern California. Today I'm very happy to introduce my recent work on 70 ASL achieving 1 mm isotropic and higher resolution with whole brain coverage using 3D TFL Picasso and a stack of spirals. I have nothing to disclose. ASL is a perfusion imaging technique well known for its non-invasiveness and low SNR. The typical imaging resolution is isotropic 3 mm. Luckily, at 70, the dual benefits of intrinsic SNR and the prolonged T1 give us another chance to push the resolution of ASL. However, we are also facing the common challenges at high field, which makes it difficult to get a whole brain high resolution ASL imaging. Here we proposed a Picasso sequence using turbo flash sequence and a stack of spiral sampling. The K-space is acquired in 12 segments. Rotated golden angle and random KZ sampling are used. We have optimized the labeling and background suppression for 70. We also used a 2 minis pre-scan to get a global frequency shift around the labeled arteries and applied it as a linear ramped phase in our labeling. In each echo, there is a RF spoiled grading echo with an asymmetric RF and a spiral grading. To reduce motion artifact due to the need of more segments for high resolution, our sequence enables sparsity in both spatial and temporal dimensions. We use the dynamic compressing reconstruction where the 12 segments are divided into 3 frames to reduce the temporal footprint and prevent inter-segment motion. And here is our 1 mm ASL imaging protocol. We have 1.5 second labeling and 1.8 second post-labeling delay. We have a short TE of 1.7 millisecond. ASL TR is 7 seconds and 12 TRs per label or control acquisition, and every 4 TRs we get an image. Previously, we made a Cartesian version. The reason we moved to spiral is spiral's higher acquisition and SNR efficiency, short TE and less ASL signal decay. Spiral is also more robust to motion and better take advantage of hardware upgrade. We demonstrate those advantages with a digital phantom. First, the spiral can use 2 times higher flip angle than Cartesian and avoid excessive blurring. Then with simulated noise, spiral achieve much higher SNR than Cartesian. Also with simulated motion, spiral has less artifact. There are also some technical challenges with spiral sampling. First, we use the curve to correct for grading errors. Second, we use MFI to correct blurring caused by off-resonance. Finally, we avoided exciting fast signal with a designed RF pulse. Here is the M0 image we get from the sequence where you can appreciate the difference made by the corrections. The corrections also bring a change in perfusion image. As you can see in the insights, there is a gradual sharpening of the detailed perfusion. This is our 1 mm ASL acquired in 10 minutes with test retest. Compared to Cartesian, the proposed spiral TFL Picasso achieves significantly higher SNR, and the ASL image has a level of detail and accuracy comparable to structural scans. The improved SNR translated to 2 times higher SAC in test retest scans. We also compared the 71 mm ASL with 3T Grace at 2.5 mm resolution with the same scan time. The improvement on spatial resolution can be easily appreciated. The labeling efficiency we achieved at 70 is 85% in overall relative to that of 3T. To examine if our sequence can capture laminar CBF, we did a finger tapping task and compared the result with the zoomed grid that was also previously proposed by our group. The result shows both sequences can capture the double peak in M1. The difference is that now we have a whole brain coverage. With this technique, we can get the laminar CBF profile across the whole brain, which can be a surrogate to some physiological parameter that cannot be directly measured in vivo. For example, vascular density. Here are vascular density in V1 and M1 measured by a microscope from a literature, where V1 shows the peak density closer to a white matter. In our laminar CBF profile, the same trend was found. Also, cell density would be correlated with CBF. We obtained the laminar profile of cell body staining intensity from a big brain atlas, and we found a close correlation between the two, while T1 and MP2 range as the control do not have such a correlation. Finally, our sequence is capable of taking advantage of hardware upgrade. We had a great experience on Dr. Feinberg's group's NexGen 70, where we used a 3 times higher Gmax and slew rate than Terra. The faster gradient allows us to use fewer spiral shots and thus higher temporal resolution. On NexGen, we can achieve single-shot 1 mm acquisition with a temporal resolution of just 7 seconds. With the improved temporal resolution, we tried some functional MRI, like visual two-back working memory task. The CBF difference between task and rest shows the activation in brain areas, and we got p-value map, which is well matched the literature. Another benefit of faster gradient and fewer spirals is that we can add additional segment along z direction, um, and that will reduce the trade-off between the flip angle and the signal decay. On NexGen, we can achieve 50% higher SNR with increased flip angle. So comparing the one we acquired at our R site and the one acquired at NexGen 70 demonstrates the higher SNR. We also spent 30 minutes to further push the resolution to isotropic 0.8 mm and got this beautiful high-resolution whole brain perfusion image. Finally, I would like to acknowledge the support from our team at USC and the great collaboration with Siemens and Dr. Feinberg's group, and thank you for listening.